How about if I do this?
Okay.
Okay. All right, so scary bird, right? You probably heard that real analysis is hard, right? So why should you take real analysis? I'm going to give you some general thoughts about what real analysis is and what kind of skills are you going to you are going to develop that are going to be useful in high school, and then we are going to look at maybe one thing where your intuition, in fact, about something you better know continuity is going to be corrected by this course. So let's just get started. So first of all, general thoughts. I think it's always a good idea to know a little bit more than what you are teaching, right? I mean, I think you expect us to know more than what we are teaching during class, right? So the same way your students are going to expect you to know more. And someday maybe a bright inquisitive student will walk up to you and ask an impossible question. And then you're going to be grateful that maybe in one of your higher level courses you actually thought about this question and then you're able to answer it. So theorem proof classes will hopefully provide you some framework when a deeper question comes along. So move on. I also believe that teaching is not about teaching students to actually do problems, but also to ask the right questions. And maybe that's even more important, to teach students, what are the right questions or what are the interesting questions. And I also believe that teaching mathematical reasoning is more important than covering every possible topic. So let's move on. So these are the reasoning abilities developed in real analysis, and I didn't run out of ideas. I could have put two more, twice as many, on this page. It's just that I ran out of room. So generalizing from specific examples, real analysis is sort of like going from a very concrete word, which is the real line and functions on it, to abstracting some concepts that make you understand these things deeper. So it's sort of in between specific and abstract. So it's a very interesting training ground for abstract thinking. You are going to learn to move from intuitive notions to the rigorous, because this is what real analysts had to do when they formalized calculus and made it a science. You are going to learn something that's very important, finding common structures in theorems and proofs, forming connections between seemingly unrelated concepts, seeing how a subject develops through a sequence of theorems. You're going to find in real analysis, after one semester, you see that there is only one big theorem. Everything is equivalent. So, I mean, it's good to see that. You're going to formulate problems, reduce difficult problems to simpler ones, analyze what is required to solve, recognize a valid proof, detect incorrect reasoning, learn from mistakes, and you're going to make a lot of mistakes in real analysis. So you're going to, this is really an excellent training ground from learning from your mistakes. You're going to look at what you achieved by not working what you wanted. You're going to construct proofs. Often you are going to pursue, and we do that in class, we pursue incorrect paths, and then you're going to find out what you learned from that and how you can adjust your proof so that it's actually going to work. And most importantly, you're going to face a lot of difficult questions, and you're going to actually learn to persevere in the face of difficulties. So I think that's a very important trait that you want to impart to your students. Move on. So why real analysis? So here it is, end of 19th century. Calculus has been developed for the past few hundred years, and we are at a state when people are making calculations like this. Can you look at this? What's wrong with this calculation? Anything wrong with this calculation? I hope nothing wrong with the algebra unless I made a mistake, right? So, but what's?
Do you need to define that the delta x cannot be 0?
Well, but yeah, so delta x can be 0. Why? Because you are dividing by delta x here, and at the end, what do? We set delta x equal to 0. This is what people did. They actually talked about infinitely small delta x's, which suddenly they were infinitely small and non-zero, and then in the next line they were 0. So what happens in 1734, an English philosopher, Berkeley, is writing actually a whole pamphlet against analysis, against people who are doing analysis or calculus at the time. And if you look in the title, it actually says, a discourse addressed to an infidel mathematician wherein it is examined whether the object, principles, and inferences of the modern analysis, that's calculus at the time, are more distinctly conceived or more evidently deduced than religious mysteries and points of faith. So Berkeley actually claims that calculus is like a religion, because we really don't know what are the principles and when delta x is 0 and when delta x is not 0. I mean, it was a complete hodgepodge of methods and arguments, and they were very obscure. It got to the point when the German philosopher actually wanted to claim calculus as part of philosophy because the methods were so unsound. So then there was a movement in mathematics at the end of the 19th century, led by some other German mathematicians, Cauchy, Weierstrass, and some other people, to rescue mathematics from philosophy, okay? To reclaim mathematics, calculus as a part of mathematics, to make it precise enough to be able to use the term mathematics for it. So this is what's happening. And so real analysis, basically, this precise redevelopment of principles of calculus without doing things like this calculation over there. So, all right, so I think we could move on. And it's going to be difficult. It's probably the greatest achievement of Western thinking, so it is going to be difficult. It has to be. So now I'm going to show you some examples for why you need to know more than your students, okay? So here is one example to be able to answer some deeper questions, okay? So this is a very familiar topic from Calculus A. We define the tangent line to the function fx at the point AFA to be that straight line through this point whose slope is equal to what? The slope of the tangent line is equal to the what? Calculus A. What's the slope of the tangent line? That's every student should know. It's the derivative of the function, right? So the slope of this line is the derivative of the function, right? F prime at A, which is basically equal to the limit as delta x goes to 0 of f of A plus delta x minus f of A. This was the quantity, by the way, calculated on the previous page for the x squared function, right? If you notice, the derivative was calculated to be 2x. Is that okay? All right, so tangent line is used later, called linear approximation, to approximate future values of the function because we are claiming that the function value at a later point near A is going to be very similar to the function value on the tangent line. Is that okay? So the line is used to approximate the function. This is standard calculus A thing. So if you ever teach calculus, you're going to do this, okay? So here is a conversation. I asked my students, it was a discussion on Canvas. So I asked this question, why is the tangent line a good approximation of the function for small delta x values? Okay, it's a good question. It's going to be a lot of clicking on this thing. So one of my students said this. Since both the tangent and the function are continuous functions at A, so what the student says is here is the function and here is the tangent line. And both are continuous functions. And their values equal at A, right? And therefore he argues that because both are continuous, if I change the x value by just a little bit, continuity is assuring us that the function value here is going to be very similar, right? This value is going to be close to T of A, right? This is f of A is also equal to T of A because the line goes through that point. And he also said that f is continuous, so the function value at this point is going to be very similar to FA also. And so since this value is close to this value is close to this value, and this value is close to this value, they have to be close as well, right? Like I'm close to you, right? I'm also close to you, therefore you guys have to be close to each other. Is that okay? That was the reasoning, all right? So notice that the reasoning doesn't say anything in particular about the tangent line, right? Because if I put any lines through this point, it's still true that this is a continuous function through the same point, right? And the values, so the function value for the SX line will be close to FA, right? And FA plus delta X is close to FA. So these 2 points have to be close also, right? So the reasoning had nothing to do with why the tangent line is special. Why do we use the tangent line to approximate functions? Why not use some other secant lines through that point? Is that okay? So next. So then I said something like, but your reasoning applies equally to any secant lines through this point. Therefore, according to your argument, we could use any other lines through the point in approximating the function. Could we really? The student said, no, I believe that not all lines through the point approximate f of x equally well. And I said, you are right. And then the student said, but then how do we know that the tangent line is better than the others? Why on earth is the tangent line better than the other lines, right? Okay? I mean, there is a question. In fact, you should be able to prove to your students that the tangent line is the best approximating line. Namely, it approximates better. But what does it mean to approximate better? What do we mean by that, right? And so, like in real analysis, we have like 3 pages just on that. Just understanding why the tangent line is the best approximating linear function at the point to a given curve is 3 pages. It takes a while to understand that, and it's not in your calculus books. Do you really want to know that? I think you do, right? So let's move on. Here is another one. Why do you want to know more than your students? Because you want to know what is right and what is wrong. And in calculus, sometimes students are going to do stuff, and it's just going to be either you're going to know what's right or you're not going to know. Is that okay? So like, look at this argument. And this was given, like, this is why analysis was in such poor shape, and even at the end of the 19th century, because arguments like these were freely given by mathematicians. So they would sum up series and get like crazy results. So here is the following series, which you all know. This is the alternating harmonic series, right? Okay? And so what this particular student did, he just rearranged the terms a little bit. Is that okay? So, so what you do is you move the 4 in front of the 3 and the minus 1/6, right? So, so you move minus 1/6 and minus 1/8 in front of the 1/5 and so forth and so on. So if you do this rearrangement, you get 1 minus a half is a half, right? You get a third minus a 6 is a 6, and you get a 6 minus a 4th. I'm sorry, what am I doing? It's a 6. And then these 2 terms, 1/5 minus a 10th is minus 1/10. And what we see here is that this is exactly the half of the original series. So if you teach calculus, you see it's going to be something like teaching blind people see. All right? Students going to look at these 2 things, and they're going to see the same thing. They're not going to understand why we need a theorem, because they're going to assume that these are automatically equal. Okay? So do you want them to calculate a bunch of limits for continuous functions where the limit exists and just keep those calculus books are you going to find are filled with mistakes? So this is like, you would make them calculate. 2 of these going to be equal. The third one's not going to be equal. And then you want them to reflect about why are the things that are equal, equal, and why are the things that are not equal, not equal. Is that okay? And then maybe you can ask a follow-up question. Could we move on? You could ask, comment on this. And then the last one would be, is there an example when all 3 things are different? This is different from this is different from that. And then they're going to understand a little bit. They're not going to understand, you're not going to be able to prove this in high school. But at least they're going to understand, right, that theorems are not true or false. Theorems are true under some conditions. And I think it's a very important thing, just to understand what we are talking about. Okay, so let's move on. All right, so my greatest selling point is really this. And I chose this picture because it really speaks volumes about what real analysis is going to do to you. And it's going to improve your vision. Okay? I mean, predator birds have like 8 times better vision than us humans. And if you do real analysis, trust me, you're going to see the bird in a completely different way. So let's move on. So you come away from a typical calculus class, right? And then you see continuous functions looking like this. Nice, monotone on subintervals, continuous graphs, right? And then they even say in these books that continuous functions are the ones where you can graph it without lifting your pencil. I can never figure out what on earth does that actually mean. Okay, so maybe you see something like this, which is crazy. It already tells you that not every continuous curve can you draw without lifting your pencil, because have you ever tried to draw x sine 1 over x? Can you draw this? No, nobody would ever be able to draw the function graph, right? Okay, so I mean this is actually a very, very stupid, outdated 400-year-old analogy that somehow never got removed from the textbooks, okay? Even the Riemann integral is not going to shy away from discontinuity point. You can integrate discontinuous functions. Is that okay? It's just the terminology is so outdated. It's 400 years. And I really believe unless we change your thinking about these things, these are going to stick into these books and nobody's going to write better ones. Because who should write the better books for the students, right? I mean, do we want to teach exactly like 400 years ago? I mean, and why all this revolution in mathematics happened, right? Why did these people actually, thought about these in a precise manner if we're going to use, 400-year-old stuff in calculus? Okay, so let's move on. You're going to see continuous functions maybe having this one example about the absolute value function, not differentiable. So you're going to see maybe continuous functions that are not differentiable at a few points, right? But that's going to be your concept of a continuous function. A continuous function is something like this that I can draw without without lifting my pencil, right? I mean, what is your concept? What is your intuition about continuity? I mean, isn't this something like that? All right? Now, if you come to real analysis, you're going to build a completely new conceptual understanding of what continuity is all about, because it's not this. I assure you about that. So let's move on. Okay, see, this is directly from the calculus book. I'm teaching from the Stewart calculus book, 8th edition, and this crap is still in there, okay? I mean, it's unbelievable. So this is how about this as a metaphor? Continuity is an opportunity for good close-up family pictures. This is actually much better than the first line, okay? So if you want to say, have a metaphor, here it is. Because what is continuity about, okay? Well, you might understand this, that nearby values are mapped nearby x values are mapped onto nearby y values. But what does that really mean? It means that if I want to take good close-ups of neighbors of this point A, I'm able to do that, right? So every time you give me like a zoom in terms of the height of this box, I can zoom in and take a close-up picture so that all the nearby family, right, the nearby values A, I call them the family, are in the picture. So you can take, more and more focused shots of that point with all the family members. My family members are, I call someone a family if it's in a small neighborhood of A, right, are going to be still in the pictures. You're not losing anybody. Okay, so, all right, let's move on. And if you use this notion of continuity, you can easily come up with constructions that are going to create very interesting continuous curves. For example, is there a monotone increasing continuous function on 0, 1 whose length is 2? Okay, now that really defeats any kind of intuition, because if you're going up like this, right, the horizontal length between 0, 1 is 1, and you have to go up from 0, 0 to 1, 1, say. Okay, it looks like the most you could do is travel something like that. To get an arc length of 2, you have to go horizontally the whole segment and vertically the whole segment, and that wouldn't be a function. So it's kind of hard to imagine how a continuous curve could do that. Or is there a continuous function, move on, easy, that is not differentiable at any point, right? You come from calculus thinking about continuous functions that are like having maybe a few points when it's not differentiable. But in fact, there are continuous functions that are not differentiable at any point, and these are very easy to construct. So let's look at some constructions. So we can actually construct continuous functions directly as a sequence of pictures. What I'm going to do, at each point I define the function value as an intersection of little frames that are just zooming onto the point. So here's, for example, the construction of the Canner function. What I'm going to do, I'm going to divide the 0, 1 interval into 3 equal rectangles like this. So there's a rectangle here, rectangle in the middle, rectangle on the right. And I'm going to keep the lower half of the first rectangle and the upper half of the last rectangle. And this is going to be our pattern, and in between I'm going to connect with a straight line. So at the next stage, I repeat this exact same thing. I cut this into 3 parts, I cut this into 3 parts, and I'm keeping the lower left and the right upper half of those rectangles. Is that okay? And I connect with straight line in between. You keep doing this. Let's look at the later iterate. To keep doing this, you see the height of the boxes go to 0, so at each point, the intersection point is going to be a single point, right? So it defines the function. So this is a function on 0, 1, and you see wherever you look at it, it actually moves horizontally. You can actually see that the length of these horizontal segments adds up to 1, which means the function is only moving up on a set that has absolutely no measure, because on the whole interval, basically, on the length of one segment, it always moves horizontally. And it still gets up from here to here. It's a monotone increasing function. The derivative is 0 almost everywhere, and the length of it is 2. Okay? Or you could do a similar construction. For example, this one. Okay? If you always believe that continuous functions are built of monotone segments, here is one that is going to cure you from that disease. Okay, so here is my pattern. Okay, I'm going to play with this. I'm going to copy now this pattern into every single one of these rectangles. Sometimes I turn it upside down. So why don't you, this is the second iterate, right? And then you look at the later iterate. And basically what this function does, on no subinterval, it's ever monotone. It always goes up and down on every subinterval. So it's not never gonna just go in one direction. So it's not monotone. Okay, go back. Right. It's not monotone, and you know the rectangles are a lot skinnier than how tall they are. So basically what you're going to do, if you have a point on the graph, you will be able to come and approach that point with other points where when you connect them, the secant slopes are so steep that you're going to get the limit of them infinite, which means it's not going to be differentiable at any point. So continuous functions are not differentiable, and if you have the right kind of intuition about them, then you can come up with very simple constructions that's gonna prove that. So, all right, so that's just one thing, but you're gonna think about other calculus concepts in a very different way, and I really think your vision, your eyesight is going to improve. So, that was my 20 minutes. I have to go to the Gloria Steinem. I hope some of you are coming. Gloria Steinem is on campus speaking from 4 to 5 in Kendall Hall. So, all right, so much more interesting than this, I hope. So any questions? A little overwhelming, right? No, I did a PowerPoint so that we can maybe put it somewhere as a resource. I also have if you wanted to learn about the tangent, advise that the best approximating function, I have handouts, so yeah, it's never...
Yeah, maybe that should eventually make it into a calc book so that it's not like average that.
Yeah.
Wanna go? Sure.
Yeah. Another reason to do real analysis, to rewrite the calculus books. I really like someone to undertake that at some point.
Okay, thanks
Yes.
for coming, everybody. If we could just give a round of applause for all the So before you guys all go, I just want to let you know that next week, Dr. Safi is returning from the University of Central Florida to give a talk about modeling mathematics. So if you guys are interested, it's next Thursday, March 10th, 2 to 3 in room 117.